All right, we're now recording. When we left off last time, we had just been discussing the upper negation identity. I had offered you a proof that worked for any positive integer and suggested that you could, with the tools we have, come up with a quick, reasonably quick algebraic proof for why the upper negation identity worked for any real number. For those of you following along with the notes, we are about 2/3 or so of the way down on page 29. I'm going to start example 331, which is find the coefficient of x cubed in 1 plus x to the minus 2. All right, so what are we using here? We're using our extended binomial theorem. So 1 plus x to the minus 2 is equal to the sum as n goes from 0 to infinity of u choose n, u in this case is minus 2 x to the n. So the coefficient of x cubed is just -2 choose 3. -2 choose 3 is not a sufficiently simplified answer. So let's use our generalized binomial coefficient identity. This is -2 to the 3 falling over 3 factorial. -2 to the 3 falling is -2 times -3 times -4. 3 factorial is, of course, 3 times 2 times 1, if you like. But what we're going to get here is -4. Example 332 says, if 1 plus x to the 1/3 is the ordinary generating function for AK, find A2. So we're just finding the coefficient of I skipped some letters here. X squared. So same thing, that's going to be 1/3 choose 2. 1/3 choose 2 is 1/3 to the 2 falling over 2 factorial. Hold on a second, this pen is wanting to go on me. So that's equal to 1/3 times 1/3 minus 1 over 2. 1/3 minus 1 is -2/3 over 2. So that's going to be equal to -1/9. So your generalized binomial coefficient problems or your generalized binomial theorem problems, they're this easy. I mean, we might ask you to write out a few terms of that ordinary generating function, in which case you have to do this for a few. Yes, Chris says choosing 2 items from 1/3 of an item feels so weird. We are a little bit past basic counting here. I will say that some of these things do model something that is kind of counting related, more probability related, which is kind of interesting. So you do get some still counting like properties. I don't actually know for the binomial coefficient here, what exactly those are. I know it's not a simple choice. But the number of ways you can do it is apparently -1/9. So there you go. All right, example 333 and 334 are slightly less related to this extension of the binomial theorem. So 333 says we have a quiz with 2 5-point questions. How many ways to get a score of 7? Now, there are some assumptions in this problem. I think I pulled this one out of the book. I'm not 100% sure. So you can only get integer scores on each problem. You can get 0, you can get 5. So the generating function for this is equal to, well, on the first question, you can get a score of 0, a score of 1, a score of 2, 3, 4, or 5. And on the second question, it just repeats. And so the number of ways that you can get a 7 is equal to the coefficient of x to the 7th in that expansion. Now, this one, ooh, we just got blurry. I lowered my camera a bit yesterday, so it doesn't get quite as blurry when it blurs out. And also the text is bigger, hopefully, anyway. So this one is probably just as easy to do by basic inspection. So what do we get here? We get the coefficient of x to the 7th. This can't happen when by getting 0 points on the first question, right? You have to get at least 2 points on the first question. And so there are exactly 4 ways you can get 2 points on the first question and then 5 on the second, 3 on the first and then 4 on the second, 4 on the first and then 3 on the second, and then 5 on the first and 2 on the second. And so 4 is the answer. And using generating functions here is just a little bit much. But if we did multiply this polynomial out, that's exactly what we would get. Sometimes it doesn't matter if we let these go on forever, but in this case, it would have changed our answer, right? If it was possible to get 6 points on the first question, that would change the number of ways to get 7 points total. So in this particular case, this is really just kind of a review problem from a couple of lessons ago. That's how you would write that generating function. And then what about example 334? Let P and R be the number of ways, number of partitions of an integer into exactly R parts where order counts. So what's a generating function for this guy? Well, let's think about each of our R parts. So we have to have something in each of the R parts, so it's got to be at least a 1. Can't be a 0, because that doesn't count in a partition. But it could be a 1, or a 2, or a 3, or so on, up to x to the n. And I need to double check something here. Give me a second. Yep. It can be anything up to x to the n, but because we don't care what happens past that, we're going to let it keep going. If it's x to the n plus 1, then we know that doesn't match one of the ways, but we also know that that won't give us a coefficient of x to the n, so we can just let this keep going. And so we get this generating function for each of the R parts. Each one has to contain something. You can think of it as empties or not okay. And so we get this to the R is our generating function. And so then each of these is just x over 1 minus x, and then to the R, right? That's obvious, isn't it, that this is x to the R times 1 plus x squared, and so on to the R. And B says, give a formula for this. So that means we need to find the coefficients. Well, let's see. What do we have? We have the coefficient of x to the n in x to the R over 1 minus x to the R. But this is the same as the coefficient of x to the n minus R, that's an n, that's an R, in 1 over 1 minus x to the R. That's essentially just saying, well, whatever this coefficient would have been, we get x to the R times it, so we can divide out that x to the R, x to the n minus R in this guy. So this guy here has coefficient what? Well, let me flip back. Oh, where did I put that page? Hang on. There it is, to our binomial coefficient. So 1 plus x to the u. So this is 1 plus negative x to the r. So this is equal to the sum as n goes from 0 to infinity of, sorry, that's a negative r, choose n times negative 1 to the n, x to the n. Chris, did you answer that for yourself? Cool. Yeah, it's natural to just think I'm pulling an x out, but it has to be an x to the r. All right, so we're looking for the coefficient of x to the n minus r in this guy. The coefficient of x to the n is minus r choose n, so x to the n goes with minus r choose n times negative 1 to the n. So if I'm doing x to the n minus r, that goes with, every place I have an n, I need to replace it with an n minus r. So this is negative r n minus, choose n minus r times negative 1 to the n minus r. Now we can keep going, and we get, let's see, we'll use upper negation on this. So the upper negation identity says that negative, this should be an n minus r, negative r choose n minus r is equal to negative 1 to the n minus r times r plus n minus r minus 1. I'm just referring back to the upper negation identity, and I'm plugging in p is just r and n is n minus r in that original upper negation identity from page 29. And then choose n minus r. But I actually already had a negative 1 times n minus r. So if I take negative 1 times n minus r, not negative 1 to the n minus r times negative r choose n minus r, that will be equal to, these will cancel out, right? Just n minus 1 choose n minus r. And then if I use symmetry on this, that's n minus 1 choose r minus 1. So the number of ways to partition an integer into exactly r parts where order counts, which is very different than what I mentioned to you, that there were going to be a couple of times where it looked like we were getting a formula for the number of partitions of an integer. This is one of them, but we have a lot going on here. We have order counts, we have exactly r parts. This is very different than what we were looking at before. And in fact, this is n minus 1 choose r minus 1. So this has to do with the other occupancy problem, where we're placing indistinguishable balls into distinguishable cells. Okay, I used the symmetry identity. So n choose k is equal to n choose n minus k. And in our case, we had n minus 1 in place of n and n minus r. So this is equal to n minus 1 choose n minus 1 minus n minus r. The n's cancel, the r becomes positive, and we're left with r minus 1. So yeah, this is just the indistinguishable balls, distinguishable cells, empties are not okay case. So it's amazing how when you just rephrase the problem slightly, it can sound like it's one of those others. And I know, recognize this goes back to chapter 2 in our book, and we're in chapter 5 in our book, I think, right now. But, you know, that's just a different way to phrase that same problem from back there. All right. I have a page flipping problem. Hang on. There we go. Just got to flip the page the correct direction. So now I'm on the top of page 30, which I had flipped to the bottom of a stack of paper. we're going to define a different kind of generating function. This is why I've been calling the other kind of generating function the ordinary generating function. So this is definition 335. A sequence AK has exponential generating function which I am of course going to abbreviate EGF. H of x equals the sum over all your k from 0 to infinity, AK, and then times x to the k over k factorial. So the first place that we can think of this exponential generating function coming up is in a standard Maclaurin series. So in a standard Maclaurin series, you have the idea that f of x is equal to the sum as k goes from 0 to infinity of the kth derivative of f at a times 1 over k factorial times x to the k. And I split that out in a way that we don't normally. And I split that out because essentially the question is, which way does the k factorial go? And I'm going to go on a little tangent here. And it's a tangent I think I've gone on before with you guys. But we just defined one way to think of x choose r is equal to x to the r falling over r factorial. And I've told you that the falling factorial works a whole heck of a lot like just a regular power. As a matter of fact, let me switch that to k. Just k's are prettier than r's and easier to distinguish from n's. Of course, they're not prettier when I write over the r's, I guess. In real number calculus and things like that, we regularly are dealing with things like x to the k over k factorial because of this, but not just because of this. So let me show you what happens under two different operators. And one is a very familiar operator, and this is the derivative operator. You guys all know him. The derivative with respect to x of x to the k over k factorial is equal to k x to the k minus 1 over k factorial. The k's cancel and I get x to the k minus 1 over k minus 1 factorial. So this operator on, if I think of that as a sequence, just gives me the guy to the left or the guy below. Now, what happens if I take the delta operator? So the delta operator for a function, let me call it delta f, is equal to f of k plus 1 minus f of k. Kind of just the top part of the derivative, except it's plus 1 in this case, not plus h, although sometimes we do that too. So this is the delta operator. And so delta of, I shouldn't have used k's there. I'm going to switch those, x, because we're letting x be our variable. Normally it isn't, it has to be an integer to use delta on it, or at least we want it to be an integer. But in this case, I don't really care. So delta with respect to x, let's go ahead and use partial derivative or partial difference notation here. So the delta with respect to x of x choose k is equal to the delta with respect to x of x to the k falling over k factorial. We can actually look at this either way. We're probably Let's look at it using the falling factorial because we don't know that all of our binomial coefficient identities apply to this generalized binomial coefficient. They actually don't all apply. Symmetry is the one that is the worst, though, and we're not going to use that one. The Pythagorean identity, the triangle identity, the binomial coefficient, Pascal's triangle sort of thing, that's that still applies, but we can actually do it straight from here. So this equals x plus 1 to the k falling minus, over k factorial minus x to the k falling over k factorial. Now, what does that look like for us? Well, this is equal to x plus 1 to the k falling is x plus 1 times x minus 1 all the way down to x minus k plus 2, right? Because I have x plus 1 minus k, then plus 1, and I've just moved the plus 1s together. Minus, I'm going to write this all over 1k factorial for now. Minus, this is x times x minus 1, and so on, all the way down to x minus k plus 2, then x minus k plus 1. So this is equal to, I'm going to factor out all of the common factors here. I get x times x minus 1 all the way down to x minus k plus 2. All of that is in common. And then what's left is x plus 1 minus x minus k plus 1. All of that is over k factorial. So this guy here, this is just x to the k minus 1 falling, right? I can rewrite this as x minus k minus 1 plus 1. And this guy here, x minus x goes away, 1 minus 1 goes away, is just k. So it's x to the k minus 1 falling times k over k factorial, which is equal to x to the k minus 1 falling over k minus 1 factorial, which is my binomial coefficient, x choose k minus 1. So where was that previous page? Right here. So the derivative of x to the k over k factorial is just x to the k minus 1 over k minus 1 factorial. And the delta difference of the binomial coefficient, which is that x to the k falling over k factorial, is just x to the k minus 1 falling over k minus 1 factorial. So these guys, these falling factorials with the k factorial in there, behaves exactly the same as these guys do, but under different kinds of derivatives. So this is your standard Calc 1 derivative, and this is not technically a derivative, but it's a derivative-like operator. We call it a difference operator. And we can play these games all day long. And these operators are very connected, and the falling factorial and the standard monomials play the same role in those two different kinds of calculus. And you get different results. So then the next thing that's natural to assume is, well, it is good to have the divided by k factorial in there, because now I'm talking about a binomial coefficient. And so in some ways, this guy behaves like a binomial coefficient does in some ways. And other times you really want to emphasize, no, I'm looking for these guys, one of those or something else. I'm looking just for the polynomial. And the k factorial, that can go over with the sequence. And so you end up, well, you know what, let's talk about that. The sum as k goes from 0 to infinity of n choose k x to the n. That is the standard binomial theorem. We can let n be not an integer here. That's why I'm summing to infinity. Otherwise, once k passes in, if it is an integer, then these are all zeros, so it's okay to say that anyway. So if n is an integer or not, this is all right. But this is just the sum as k goes from 0 to infinity. This is n to the k falling over k factorial x to the n. Now, if we played with this a little, I'm sorry, I've said the wrong, this should be x to the k's, right? That is how that works. If those were all x to the n's, that would just be silly. Those are all x to the k's. If we play with this just a little bit, then we get the sum as k goes from 0 to infinity of n to the k falling, and then x to the k over k factorial. And you see now this is behaving like my polynomial, my monomial, and this is behaving like my binomial coefficient. And so there's some degree of interchangeableness. Where do we put the k factorial? And I know that seems very, probably seems pretty out there right now, but like half of my dissertation was playing around with where does the k factorial go, and which of these are we thinking of as our kernel, and which of these are we thinking of as our binomial coefficient. And another place that this really comes together is in e to the x, right? E to the x is just the sum as k goes from 0 to infinity of x to the k over k factorial. Well, if I take the sum as k goes from 0 to infinity of x to the k falling over k factorial, or we can look at that as, oh, too close, the sum of x choose k as k goes from 0 to infinity. Any ideas what this is going to be? Anybody remember that binomial coefficient identity from somewhere? Specifically here, if x is n, if it's an integer, then this is the row sum identity of of our Pascal's triangle. So it's just 2 to the n, but it works even if x is not an integer. And real quick, what's the derivative with respect to x of e to the x?
E to the x.
Yeah, it's just e to the x. And what is the delta operator on 2 to the x? This is equal to 2 to the x plus 1 minus 2 to the x, which, since that's just twice this, is just 2 to the x. So you have this kind of parallel calculus. You have a discrete calculus and you have a continuous calculus. And whether you think of this as a binomial coefficient, or you think of it as some sort of a monomial, a kernel of our polynomial space, like this was, you get these weird analogous results. Now, I didn't play with just standard discrete and standard real calculus because those are well explored. I actually played around with harmonic calculus, which is not the name of the thing. There's another thing called harmonic calculus because they stole the name before I got there. But calculus on the set of harmonic numbers. It was a lot of fun. But anyway, that's this notion that for the idea, I'm back like 3 pages now. Where did we go? To our exponential generating functions. So the exponential generating function treats the k factorial as part of the kernel, as part of the basis set of polynomials, whereas, and so then the sequence is the coefficient of x to the k over k factorial. And since we were dealing a lot with Maclaurin series, many of these are pretty straightforward. So, and I know we're getting close to time here. I'm going to do just one example. E to the x. E to the x is the sum of x to the k over k factorial as k goes from 0 to infinity. So this is the exponential generating function for, well, the coefficients of x to the k over k factorial is just that sequence of all ones. So whereas 1 over 1 minus x, which was the sum as k goes from 0 to infinity of just x to the k, is the ordinary generating function for the same. So that's what's going on here with exponential generating functions, is we're going to get a new generating function because we're thinking about what happens with that k factorial. We're factoring it out, basically. Time for one last one. 1 over 1 minus x equals the sum as k goes from 0 to infinity x to the k is the exponential generating function for, well, it might help to write it this way. That would be the sum of k factorial times x to the k over k factorial as k goes from 0 to infinity. So that would be the sequence k factorial is the coefficient sequence when you think of this as an exponential generating function. And we're doing that just to manipulate the sum. There's very little reason except just to play with this and learn about it, to think of this as an exponential generating function. There is every reason to think of this as an exponential generating function, but we'll do more examples next time. Any questions? Did anybody time it while I was geeking out about Pauling factorials being like regular polynomials? It's probably at least the 3rd time this class I've done so. So you guys, have you turned it into a drinking game yet?
Not quite.
Yeah, it's just something I think is really cool.
It is interesting learning about.
All right, well, you guys have a good day.
You as well.
And I'll see you on Monday.